Hello everyone. Hello everyone. My name is Jani Basha. I am an AI researcher at Cellstrat. Today we are here to discuss and learn about the latest state of the art text to video generation model Sora. So let's get started. So before getting jumped in technical part of it, let's start with the some example videos generated by Sora model to get some excitement and interest in the ongoing presentation. So let me start with the first video here where the cat is trying to wake up his owner or her owner. So we can see like how realistic the video is. It's not like the past video generated models. So the furs and then the human textures and then all the other things are very uh, accurate here and then very clear. And we have one more famous video from our OpenAI website, so where a woman is trying to walk on the street, and we can see all the shadows populated in the water, and also background people moving. So these two are the few examples that are generated by Sora model. Then like to understand this model, to understand this Sora model more better, like how is it able to generate this much clear and then quality videos. We need to understand its technical capabilities, like how it was built and then what is the technologies involved behind. So let's start with that. So to understand the Sora model, we need to have the deep understanding of stable diffusion and then the farmers. So these are already new to us. We are these two are not new for us. They have used these existing papers only to develop this Sora model, and we'll briefly discuss about these two model before getting jumped onto the Sora model. And this Sora model is publicly still not available. It's not available for us to test, and also the code also not yet released. So that is one disclaimer before going ahead. So let's try to understand the stable diffusion model first, which is the main architecture uh, behind this Sora model. So this Sora model is this diffusion model. I'm sorry. So this stable diffusion is based on the paper called high resolution image synthesis with latent diffusion model. So this first part is clear, like high resolution image generation, and the second part of that paper name is tells like latent diffusion models. So we first need to understand this latent diffusion models. So what are latent diffusion models? So, in this latent diffusion models, there are two main, like there are four different things that we need to understand first to understand this latent diffusion models and their techniques. So there are two different CNN models in that latent diffusion model. So one is a variation autoencoder, and one more is a um, so one more thing is a unit. So unit is like let's before understanding these two models, why we are using these two models, let's get started to understand the process of forward diffusion and reverse diffusion. So the first forward diffusion is nothing but image destruction process. So we'll try to destroy the existing image, original image of a dog or maybe cat, anything from our data set. And in the process of reverse diffusion, we'll try to restore that destroyed image. So that's how let's see how we do that forward diffusion and reverse diffusion process. So in the forward diffusion process, as I said, we'll be destroying the image. So that for that we don't use any CNN model. We'll just add some Gaussian noise to the image. So let's take some image of a dog. We'll iteratively add some Gaussian noise at each step. So at initial stage, we'll add noise to the image, and then like uh, iteratively we'll add more noise. At the end of the maybe 100 or 1000 steps, that image becomes non recognizable. So we will not be able to say that what is there in that image. So whether it is a dog or whether it is a cat, that we can't say. So that much level, we that much of noise will add in the forward diffusion process. So once we, after adding that noise to the image, we'll send it to the reverse diffusion process, where the model predicts that how much noise was added in the previous step, that is forward diffusion. And uh, once it predicted that noise part will remove that noise from the image to generate the original image. So like how we added iteratively noise here, will remove that noise iteratively from uh, in the reverse diffusion process. So as I said, for adding noise, we'll not use any neural network. We just use Gaussian noise. We'll add that noise image. And for reverse diffusion, for removing the noise, we use the unit model here. So as I said, in the reverse diffusion process, we'll be predicting the noise using the unit, and we'll remove that noise to generate the original image. So this is the complete process of diffusion model. So these steps, we can say that the process of uh, diffusion models, where iteratively we are destroying the image, and we are restricting the uh, restoring that image in the reverse diffusion process. For this reverse diffusion process, we'll use the noise predictor unit model for generating the noise, I mean, for generating the original. So in the data set, we'll have so many different model images. So when we start with some random noise and try to remove iteratively noise from that image, that time we the model can generate some random image. So we want to control that randomness. So like if there are some thousand different kinds of images in the data set, when we give it to the unit with the some random noise, it might generate any random image out of those thousand images. So to control that, we'll add one um, we'll add one textual model, we'll embed some textual prompts and pass it to the unit, so that we are giving some conditions. So instead of generating the random image out of those thousand, I want an image of some train. So that will give as an instruction to the unit model, so that we'll embed that textual prompts and we'll pass it to the unit model um, along with the noise image. So that's how we generate the images of the some new images or some different
Yeah, I
images.
think you have an architecture diagram, right, on next slide or so.
Yeah,
So that would be very intuitive if you show that diagram.
yeah, sure. Let me go to that. So this is the process, diffusion process. So wherein like we started with uh, some real image. It's an image of a human being here. So it can be anything, maybe dog or something, train or something. So as you can see here, iteratively we are adding the noise. So at step one, we have added some noise, and step two, we have added some other noise. After a few steps, we can see that image is still recognizable. So this we can say that this is the human image, even though there is some noise. So like that, we keep on adding the noise, and at the end of this maybe some 1000 or 2000 steps, this image that image initial image got completely destroyed. It became completely noise. So from this noise, this is the process of forward diffusion. So wherein like we have completely destroyed the image, and now we need to restore that image. So that restoring process we call reverse diffusion process. So wherein we started with the, this is the, like from here we started from random noise, and then iteratively we are removing the noise. So now we have like little bit of human kind of image, and finally we got to that original image. So we started from this side. So reverse decision starts from this side. So in order to do this forward diffusion, we'll use Gaussian noise. We'll add Gaussian noise to the image. So that's what I was telling. And in order to do the reverse diffusion process, we'll take the help of unit, wherein we are predicting the noise and then subtracting the noise from that image to get the original image. So unit job is to here predict the noise. So if we start with some random noise here, we can't guarantee that we'll always get the human image. So we need to give instructions to the unit, as I said earlier. So this is the unit model here. So for this unit model, I'm giving instructions by embedding or by giving prompts. So we'll give prompts by embedding them into uh, by embedding them and then passing it to the unit model. Here, along with the image as input, I'm also passing the textual prompts. So this is the complete diffusion model process. So is this clear to everyone? Is or people are having any comments?
So, correct me if I am wrong. The whole point of this activity is to eventually train that decoder, the lower half, basically,
Yeah.
which can generate an face image
Yeah.
from a random noise, right?
Yes.
So finally, we will throw away the top part, and we will only use the bottom. So upper one is called encoder. The below one is decoder, I believe. So the
Mm,
decoder will then be used in production inference
yes.
for generating images from random noise. Correct?
Yes. Yes.
Okay. Okay.
So instead of being completely random, we'll use additional prompts here to generate whatever the image that we want. So
Okay.
that is the diffusion model architecture. So in the previous slide, I was talking about latent diffusion. So what is the meaning of now latent diffusion here? So this process, if we do it on the complete original pixel space, so take we have 1024 by 1024 image size, and if you run this whole process on that uh, bigger image or HD quality image, it will need greater computation. We need a lot of computational power to reduce that computational power. We are using the uh, variational encoders here, auto encoders. So wherein before even starting this diffusion process, we'll run the variational auto encoders to uh, downsample, or we can say generate the latent space. So instead of 102, we'll compress that 1024 by 1024 image and generate one latent space, say maybe 32 by 32 image, and we'll run this entire process and that latent space. So that is maybe we can say 32 by 22 image or some other space. So that is why this model is called latent diffusion model. So instead of running this whole process on the complete image, we'll run it on the latent space. So for that, we'll use the auto encoders here to generate the latent space. So that will help us to reduce the computational power that needed. So during the forward process, I said we'll be using Gaussian noise for that. So that is this is the formula for that, wherein we took the initial image x0 and we are adding the noise here, Gaussian noise, and generating the some noise image again. After adding the noise to the original image, it will become noise again. So this is how we generate the noise image in the forward diffusion process, and we are using the unit here for predicting the noise. So we'll predict the noise and we'll subtract the noise from the image, and then we'll try to get the original image. Yeah. So if we put together everything into one image, this is how it will look. Um, like the complete architecture, wherein we started with the some random image or bigger image, 1024 by 1024 image, and we have passed it to the auto encoder or variational auto encoder, where it has generated the some latent space. So actually this image must be image only, but it is given as some noise, but actually this must be some image. So which is in the lower dimension. So this latent space will pass it to the forward diffusion process, where it will be like adding noise at each step, and at the end of some maybe 1,000 steps we'll have completely noise image here. So that complete image will pass it to the diffusion process. So where like a reverse diffusion process, wherein we'll be trying to iteratively remove the noise. So as you can see here, we are iteratively removing the noise, and at the end of the maybe 1,000 steps, we'll get the latent space. So that latent space will decode it back to the original. So this is the complete process. So in this, if we little zoom in this model here. So here we have a semantic map, and like textual conditions we are passing along with the image to the unit. And yeah, so even iteratively we'll be trying to predict the noise here. So this is
One question I have is why you have so many unit models in the bottom, reverse pathway. Why do we need so many units? So, uh,
actually this same unit, to illustrate, like I am passing it 1,000 times, maybe to remove the noise. I have given like multiple images of unit here.
oh,
So
just one unit, but you're running it multiple times. Okay.
multiple times, yeah. First time we'll pass this image to the noise image to the like, unit. Then it will predict some noise. So that noise will be removed from the image, and that new image will be passed to the unit again.
Hmm. Hmm.
So it's kind of loop.
So this is inference pipeline, right? This is not training pipeline, this whole thing.
Yeah. So this is a training pipeline only. Even inference looks similar, but inference part will not. We don't need to run this part.
Right,
Uh,
right, right.
Forward diffusion will not run. We'll just start with some
Oh,
random latent noise.
right, right. Okay. So any questions, folks? I mean, this definitely needs expertise in, you know, uh, computer vision or deep neural network architectures. So if you're new to deep learning, then this will be hard to understand, I suppose.
One question from infrastructure perspective, we know CNN needs GPU and high-end computing,
Yeah.
so the cost is huge. But I learned that the latest techniques of ChatGPT 4.0 or Microsoft's Copilot, etc., they run on a very thin layer, causing very less cost. How does that happen? If somebody can throw some light, cost perspective, how?
So I don't think that is running on some lightweight machines. I guess backend they must be having some high level machines which are generating the output in within seconds. So to reduce that latency, they must be using high end backend systems.
So the models are already run and prepared, and we just throw our prompts to get the output.
Even like for our simple prompt, that will take a lot of computation
Yeah.
in the backend.
True.
See, and one more thing, Sandeep, here is that you're talking about Chat GPT and GPT architecture. So training infrastructure is significantly many more proportions of inference infrastructure. So when we are using Chat GPT, we are merely using the inference pipeline,
Hmm.
we are a pre-trained model. So the inference infrastructure will be lighter typically compared to training infrastructure. So in training, they would have deployed massive web farms,
Hmm.
right? Google and OpenAI have large web farms. But during inference, somewhat smaller, GPU infra can handle it.
Okay.
ChatGPT is getting millions of queries and GPT API, so they would have a scale architecture, but individual prompt can be served with slightly lighter architecture. It may still involve a GPU serving capability. It may not be simply CPU, I am supposing. But when we run Llama 2 or Mistral LLM on our local computers,
Hmm.
or our local cloud like AWS or Azure cloud, then I have seen that CPU based inference works fine. It's not too bad,
Okay. Okay. Thank you.
because we are using pre-trained model. We are not having to train the.
Okay. Okay.
Yeah, clear. Thank you for.
Thank you.
So this is the inference pipeline. Before, so as I said here, we don't have the forward diffusion process here. So we are not destroying the image. We are directly starting with some latent noise image here, and along with a textual encoder. So uh, we ha- we are encoding the embedding the we are generating embeddings of the textual prompts and passing it to the unit along with the noise image. So then we are generating the original image at the end. So here you can see that loop that is going on. So each time it predicts some noise, that noise will be removed, uh, and also it will be passed back to the unit to go through again this whole process of running predicting the noise. So during the inference pipeline here you might not observe that forward diffusion process. So next we have another topic before moving to the diffusion transformers. So um, is there any questions on latent diffusion process or latent diffusion models? Yep, I'll consider the silence as no. And
I have one quick question related to videos. How does that all come together? Because this is what we're talking about, just an image.
yeah, so we'll move forward. We have the slides to talk about that.
Okay,
Yeah,
thanks.
this is still about latent diffusion only. So that comes when we start discussing about Sora. So then we have diffusion transformers. So there, here what we were doing, we used to use the unit. So and to generate the image, to generate the original image by removing the noise. So the overall concept wise diffusion transformers, everything looks same to this architecture. We'll just replace this unit part with the transformers to there are some uh, benefits using unit transformers. We have already seen vision transformers doing great things in the space of vision, like vision, this one domain. So they just wanted to make utilize of transformers in the space of vision, and replacing this unit in the diffusion models. So we cannot just simply replace the unit with the um, transformers. So when we say vision transformers, uh, there was like it was just passing the image as input and getting predicted as whether it is a dog or not. So if everybody has some idea about vision transformers were for image recognition purpose. So for image recognition, what we just need a image as input, and at the end this transformer model will predict the class of that image, whether it's an dog or train or something. So it is like a image recognition model. So when it for in order to incorporate vision transformers in the diffusion process, we also need some kind of text embeddings to this. So as you can see here, along with we are not only passing the images to the uh, unit here, we are also passing the time steps, and also we are also passing the uh, embeddings of the prompts. So we need to give that vision transformers the capability of processing both image and text. So that is the difference. So that thing we need, that capability we need to add to the vision transformers in order to work in order to fit in the diffusion model process. So that we will see how they have achieved this. So it is already proven that the diffusion transformers uh, have outperformed the unit based diffusion models. So that how they have enabled that, we'll look into it. So yeah, let's directly get started to the architecture so that we'll get some idea. So as you can see here, the architecture, everything looks same. So instead of this unit, we have replaced it with the transformer model. So this transformer, for enabling the transformers to work on the diffusion process, they have added some made some changes to the architecture. So if you have remember the transformers architecture, so there won't be this part. So this red part is the new thing. So we know that transformers had multi-headed self attention layer and feed forward layer, and like normalization layers. So whatever there in this red block here right side, that this is the new part. So this is allowing the transformers to work for both input images and taking the embeddings also as input, like textual embeddings as also input. So before going for that, so generally we know that transformers need tokens as input. So what we do, we give some textual prompts. So generally, like I'll tell that I need a dog image. So we need to generate the tokens as an like tokens from that prompt line, and we need to pass it to the transformers. But when we say images, we don't have tokens. Image is like a complete image. It has some maybe 1024 by 1024 kind of pixels. So how we pass it to the transformer model? So that, like, for that purpose, we need to divide that image into tokens. So that is the main thing that is involved here, using transformers for the uh, in the vision space actually. So here we'll see how we'll use transformers in the vision space. So as I said, so transformers need tokens as input. So for converting our image into tokens, we'll divide uh, that image into multiple blocks. So if we take this big image, for now we'll just consider it as a 4 tokens. Like we'll just extract this part as a token 1 and this part as a token 2. So they remaining as a token 3 and token 4. So these 4 tokens will extract from image and pass it to the transformer block. So along with that, we'll give the positional encoding. So this image is the first image and this image is the second image. So like this, along with this image, will pass positional encoding. So this will pass it to the transformer block. So that for doing that, they have chosen different parameters. So it will, like, you can see this example here. So if we start with the 32 by 32 image of latent space, that using this formula here, we'll get 16 tokens. So it is like our image is of 32 by 32 that we divided by p. So if we start with the maybe like 2, 4. Yeah, if we divide it by 8, consider that our parameter p is of 8, 32 by 8 is of 4, and 4 square is 16. So this 32 by 32 image is converted into 16 tokens. So these 16 tokens will pass it to the transformers. Hope I'm clear here. So why we are doing this patches, like extracting the patches here, is like, as we know that transformers need tokens as input. That's why we are also converting this image as a tokens and passing it to the transformers.
Now, Jani, why not use clip algorithm? Because clip is a very seamless transformation from text to image and image to text.
Text to image.
You know, clip is the one driving Delhi, right? Or yeah. So in Delhi, the text to image model, they have used clip. So they basically convert text into image and image into text. And the clip has been trained by correlation of images and text web pages. So I mean, it's kind of similar to Clip what they are doing here, I would think.
Clip. I'm not able to recollect that architecture of that clip. Uh,
Yeah, that's fine. That's also a way to convert text to image, image to text.
mhm.
So that was also an OpenAI algorithm actually, and they use that for Delhi 2, I think, or Delhi 1 at least. Yeah, yeah, it's somewhat similar. You want to convert image pixels into token representation,
Yeah.
which can serve like textual tokens.
No, no. Actually, these will serve like image tokens only. They'll be, yeah, yeah.
I mean, ultimately,
Like
it's a
number.
mathematical metric, so it's
Yes.
just maths, right? So yeah,
Yeah. Clear.
okay.
Clear. So like this, will generate the tokens. So if we have some bigger image, we'll obviously get the bigger tokens. So actually, there is one benefit in converting this image into tokens. So we can process any size of the image. Like if we now we have started with the 32 by 32 image, we got 16 pixels, 16 tokens. And if we start with some 64 by 64 image, we might get some more tokens. But when we like for the transformers, whatever may be the size of the image, it doesn't matter. So it is like as it is like it is looking at each token at once, or maybe bunch of tokens at once. So when we when we have seen earlier unit based backbone model, so where unit will have a strict restriction on number of pixels that is getting passed, like that is like image size. So we know that for unit based or CNN based models, that input vector size must be fixed. But by using this transformer based architecture, we'll have that flexibility of we can train the this diffusion model with any size. So that is one the major advantage that we are getting using transformers. We'll understand that more better so in coming slides. So how for this till now this conversion of image into the tokens part is clear. I hope that.
I just have one question.
Yeah.
Here. Yeah, so here, so in when we go back to CNN models, we never used to think the pixels or the images as a sequence data, right? Now,
Yes.
are we staying in DIT and with tokens coming into picture, are we treating them as sequence data?
Yes, that we are treating them as sequence of data, and we are giving that positional embedding. So as I said here, this is the first crop, then second crop, third crop, fourth crop. So we need to pass these four images as in a sequence to the model. So in order to not lose that sequence, we are also giving the model this positional embedding. So we'll tell that this image is a first part of the image, in like this image is the second part of the image. So we'll be processing in the sequence only. In
And how many
CNNs,
image?
we are not habituated to look
Yeah,
in that way. We'll be looking in uh, like convolutional networks. We have idea, right?
right. So, but how many images are there here? Means one image of 32 is fine.
Yeah.
Like that, are we saying there are so many, means there are lot many images for training
Yeah.
and
Yes, we'll have a lot many images. We can say that instead of images, we can say tokens. So we know that in the like when it comes to the textual transformers model, there also it is like tokens only. So we'll be passing some for one sentence. We might divide that into some 10 tokens and passing it in a sequence. So there is a layer called multi-head self-attention layer, which is learning the uh, relation between each token. So the same thing is helping here also. So even though we are passing all different crops in a sequence manner, the transformer's job is to uh, learn the sequence and like learn the relations using this multi-head self attention layer here. So similar to the textual prompts, how it is able to learn this complete sentence as single sentence and learn some kind of relation in that. The same way, if you even if you pass this image in a sequence also, it is able to learn that yeah, total number of sequence as a single image because of this self attention layer and other internal architecture that is involved. So now we can forget about the image as input. Now since we have converted image this image into tokens, now it's again like similar to that textual embeddings that we pass general to the transformers. Are you
Yeah,
clear?
I got it. Yeah, that helps. I think this is capturing different aspects of that image, right? Of the same image.
Yes, yes, for the same image. So this is how it works.
See, what is
So
this alpha beta on the right?
yeah, I'll come to that. So like I said, we need to pass along with the image, we need to pass the positional embeddings to the model transformer, and also we need to pass textual prompts also as input to the model to generate like whatever the image that we want. So there along with the image here, we are also passing two additional things like textual embeddings and the positional embeddings, so that we need to pass. So that how we'll pass. So generally they have tried with the different architectures. So if they simply, there are these are the two different other architectures of transformers that is used in the stable diffusion process. So one first part is just uh, just giving the, yeah, like for just concatenating image and the textual prompts and the embeddings. Like we have the 16 tokens of the image. At the end we'll also concatenate these textual embeddings. So that's like prompts will concatenate, and then we'll just pass it to the existing transformers model. So you can see here, this is the normal transform model that we generally see. So there is no architectural change here. So this is one thing they have tried. And uh, due to this there are some like even this has worked, but there are some issues like a number of computations will get increased. So if you are processing for image related tokens, additionally we are also giving the model that textual embeddings as a input, so the number of tokens has increased. So due to this, number of computations have increased. So that is one thing. And the performance is also one issue, like they have not much increase yeah, observed the not much improvement in the performance. So they have kept it aside. And that there is one more architecture wherein like instead of appending image related tokens and textual related tokens, they have directly given it to the multi-headed attention layer. So they have ultimately they have reduced the number of tokens that are getting passed into the transformers. But even this is like not much performance was not much good results. So these are all the two different architectures they have tried. So after several other researchers researching tech, they have found one more architecture which is working better. So wherein like they have introduced the MLP. This is the simple two layer neural network which will take the textual embeddings and positional embeddings as input, and produce this alpha and gamma and beta parameters, and where it will be like helpful for where it was like helpful for generating the images. So like this you can see these are all these thing also they have newly introduced in this existing transformer architecture, where it is be helpful for generating the helpful for understanding the scale and then shift of the parameters. So the this can be understood with example actually. So let me tell you, um, like our past approaches, as I said, there will be fixed size of the images that we need to pass into the neural network, maybe like 256 by 256 size of image. So in order to do that, some images or some videos we might crop them. So when we crop them, there is a chance of losing some part of the video or image. So like if if I have a image of myself of 1024 by 1024, since my model accepts only 512 by 512 size of the image, I need to crop my image and then pass it to the model. So when I crop that, there is a chances that my hand or my legs might get cut, and then we'll pass that image. to the model. So since there are this kind of images in the training process, so there are chances that during the inference also uh, we might generate this kind of images only, wherein like the person with the without hands or maybe without legs, means like cropped. So in order to do learn that kind of things, these parameters are helping, along with this like shift parameters are helping. So those things we are, instead of directly passing, like directly giving them into the model and then asking it to learn, we have added some additional layer called MLP, uh, wherein it will be generating these gamma and beta parameters to help that, to help to learn that.
The MLP is multi-layer perceptron, just a
Yeah.
basic deep neural network.
Yes.
And you are basically either adding or multiplying in, multiplied by alpha this plus that, right? So
Yes.
I'm thinking that scale and shift is adding, alpha MLP output plus whatever is there.
Yeah.
Is it a plus or multiplication when you do
Yeah,
scale?
actually, it is a plus.
Okay, they are
Yes.
adding in the scale, they are plusing this plus alpha this, right?
Yes. Yes.
Okay.
And this is a simple neural network with the two layers just.
Basically, they are conditioning the signal which is moving forward with this textual intelligence.
Yes.
And in each of those scale blocks, they are augmenting the textual intelligence moving forward with, sorry, the image intelligence moving, the signal moving forward with the textual conditioning.
Yes. Yes. So we don't need to fear of looking at this many images here. Actually, this is different techniques they have tried. Instead of directly, if they directly use this transformer model as it is, so it will become another like normal textual model kind of thing. But the main thing is with the diffusion models, we need to generate the images whatever we want. So for that we need a textual condition here. So in order, like we need to give the capability to the transformer of handling this textual embeddings. So that's why this extra layer has come. Otherwise, this complete architecture is same as what we know as transformers. So we are giving these transformers the capability of both handling textual conditioning and then image related tokens. So overall, we can, if we consider the complete block as an transformer, we can move ahead and then look at this high level architecture of latent diffusion transformers.
So one question here. So
Yeah.
can we say this entire scaling shift MLP is done for basically to normalize the text images to some auto scaling purpose before it enters into uh,
Ye- Yes, yes.
multi.
Here we can see this alpha thing where it is like before each transformer block, we'll be scaling those features that is coming out of this each network here, and even like gamma beta also, before passing the vectors that we are coming into the, like before passing them into the self attention layer, we are scaling them and then applying the normalizations. We can say that kind of.
See, basically, this is noise moving forward. This is the reverse diffusion process, isn't it?
Yeah, this
So
is.
this is going from noise to image. When it's going from noise to image, basically you are augmenting that reverse diffusion process with textual intelligence from the prompt you have given. So that you are saying that make sure that the noise to image transition includes a man in the final image. So it is incrementally adding the man intelligence as the noise moves forward back to the image. Jani, correct me if
Yes,
I'm.
correct.
So this has to be seen in the context of the larger architecture shown before, because this is, we are still in the reverse diffusion decoder process. Noise is being transmitted back so that it can convert back to a man image. So,
Yes.
but to make sure it produces a good quality man image, it has to we have said this image has a man. So that textual prompt is being augmented into the noise by this sideline pathway with alpha beta augmentation. This is what I understood.
Yeah, clear, Vivek.
What is this left diagram doing? This I didn't understand fully.
Yeah. So this left diagram is nothing but what we have seen in the previous diagram. So to understand it better, I have put it here, which we have already seen. So this image we have already seen. So if we keep it here, it will be more we can understand it better. But this is what they have given in the um, paper. So I just kept it here. So I'll explain it. I'll explain this one as well. So wherein like we are passing the latent diffusion noise image here. So you can see that what we do generally in the latent diffusion process. First we'll run the autoencoder to generate the latent space. So now we got the latent space. So that latent space image or latent space noise image, we are passing it to the our complete diffusion transformers architecture, latent diffusion transformer architecture. So we have the latent space now. So first step is to we need to patchify that. That is nothing but we need to crop the images and then we pass it to the this transformers model. So this is the second step. We have done with the autoencoder first step, and then we have patchified this, and then along with this patchified image or tokens, we need to also pass this uh, textual tokens. That is nothing but prompts. So that along with that prompt, we'll also give the time steps. So here time steps means the positional embeddings of that image. So here we are getting two things. One is the prompts and also embeddings, means positional embeddings. So those two along with this image tokens, we are passing it to the transformers block. So at the end, we'll get uh, noise predicted. So here we are predicting the noise, how much noise was added in the input image. So that we got. And along with that, we also getting some covariance metrics, which is helping us to understand how each patch is related and then how they are correlated. So this kind of information we are getting here. So this is some additional thing. So this is we can see like normal covariance matrix that we generally observe in ML architecture, ML model, ML side, which will be telling all the patches, which will be telling the information about the patches, like how they are correlated, how each patch is related. So this kind of information will be there. So this is much no need to be concentrate much, but this is the main thing that we are getting. So noise as predicted. So we get the noise. So after that, we'll remove that noise from the original image, like original input image, and we'll try to get less noisy image. So now the output that we got is the less noisy image compared to the input image. So now we pass this again back to the this our architecture, and then same thing will happen. We'll patchify it and we'll pass it to the transformer block, and we'll again predict the noise again. So this predicted noise again will be subtracted from the original noise image, that is x2 here. We can say like this is x2. So we'll remove this predicted noise from the x2 and we'll get some more x3 now again. So like this we'll run it for 1,000 times or maybe depending on the hyperparameter that we set. So the final image that we got will be the cleaner image. The same thing if we keep and understand from here, it will be more clear because since we have already seen this image. So compared to this, our old latent diffusion model based on UNet is like that is same as this one. Instead of we are just replacing it with the diffusion transformers model. So overall process is same. Only the we have replaced it with the transformer block.
Yes, yes, this makes it clear.
Yeah.
So the only change is UNet replaced by this DIT
Yeah.
block in below. Okay.
Yeah. In our previous two slides, I have tried to discuss how this normal transformers, whatever we known, is modified to work for diffusion transformers. So this is what the additional thing that we have added
Hmm.
to make it to make the normal transfer model to work for our diffusion process.
So this works better than your UNet
Yeah,
blocker.
definitely this has surpassed the results of diffusion models of unit based, and that's why we have seen another next.
Jani, this we are discussing because DIT will be used in Sora, correct?
Yes.
Okay.
So this is about DIT and stable diffusion. So these two are the main building blocks of Sora model. So based on these two models only, Sora model has built. So I can say that there is nothing new in the Sora model. So they have just used these two. They have just combined these diffusion transformers and then stable diffusion model to generate the to make it work for the videos. Yeah, obviously there will be some small changes to make it work for the videos. Since it is only for the images, diffusion transformers is only for images. Sora is for videos. There are small changes, but more or less architecture remains same. Yeah, if everyone is clear about DAT and stable diffusion, we'll move ahead for our main topic Sora and we'll try to understand that Sora model.
Yeah, yeah, go ahead, I guess.
Sure. So Sora, we know like this is a text to video generation model, and it has they have inspired it from LLMs. So we know like LLMs, it is we can use it for general purpose. So earlier before this LLMs, we need to train different models for different purposes. Like even though if you are doing that regression model of even if our data set changes, we need to train our new model again, maybe in different places also, even in NLP space also we need to train different models. But after when once we get these LLM models, we are using same model for maybe like question answering and then some kind of video text generation model, text generation use cases, and also code generation use cases. Most of if we are able to use the same model and able to get similar kind of results with the single model instead of training different models. So same thing they wanted to do with the uh, Sora model by taking the help of transformers. So like the way LLMs are doing same like multiple tasks with a single model, Sora is also able to do multiple tasks like video editing and then video generation and then some video continuation kind of works uh, with the help of this diffusion transformers architecture. So yeah, that is a little background behind this Sora model. And architecture wise, as I said, it will be same. Initially, we'll have encoder decoder architecture. It is not openly said that which encoder model they are using, but it is most of the forums it is mentioned that they are using same VAE model, which is used in diffusion transformers and stable diffusion. So they are using as is the same thing. So this is as we know like this encoder decoder is architecture is for first we get the image and we'll downsample or we'll generate the latent space of the image, and then at the end once we get the latent space we need to generate back the original size image. So we got the 32 by 32 image as an output from the Sora or diffusion transformers. We need to generate back the original image of 1024 for 1024 image. So for that we are using this encoder decoder architecture. So here also we are using same image VAE for downsampling the video and then upsampling the video. The same thing we are using. Yeah. So once after generating the latent space of the video, in this case, we'll pass it to the Sora model. In this case, we can say like here we are directly using diffusion transformers, and that Sora model generates the latent space of the video. So that latent space video is will be uh, generated like populated back to the original space pixel space using the decoder model. So it will be decoded back to the original pixel space. So the overall architecture, we can see like same thing, whatever we have seen in our previous diffusion transformers. So that's why I have started with diffusion transformers and latent diffusion model. So there are two different small changes that needed to make diffusion transformers works for the videos. The main thing is video compression. Yeah, as usual, we need to um, compress this video to generate the latent space. We know that like if you work on the original space of the video, it will we need a lot of computational requirement. So we need to generate the uh, compressed video, so that we are taking the help of encoders here again. So the difference here is, earlier we were generating the patches here. So these patches were, we can, if we ignore that channels, RGB channels, we can consider that this is an one dimensional, so two dimensional image. We have just width and height. So but when it comes to video, we'll have another temporal dimension, wherein like it is a time space. So the video will have multiple frames. Even for looking at 1 second video also, we need maybe once 1 second video also, we need multiple frames. So that is adding the additional dimension here. So that is temporal dimension. So that's why you can see that here the generated latent space is not one dimensional here. So we have multiple dimension. So we can in a way consider that each layer in the front side is as a each layer in the front side has a frame kind of thing. So this is frame 1, this is frame 2, this is frame 3. So like that we can say. But originally this is not exactly frame to frame decoding. So I mean, like if there are 100 frames in the input video, we can't say that we'll have 100 latent spaces here. So because like we are compressing this video both in terms of like depth, height and width. So like say like we have an image of 512 by 512, means we have a video of 512 by 512 by the 100, where 100 is an number of frames. We might get an output of 32 by 32 by some 10 maybe. So this kind of like both temporally will compress, and the height and width wise also will compress. So after that it is again same thing that we do, we'll generate the tokens. So maybe like we'll take this complete block as one token, this another token block as another token. So like this again we'll take this block as another token. So like this will patchify them again, same the way same as we have done in the diffusion transformers, and we'll convert them into tokens. So this part is similar to the previous diffusion transformer that we have seen. Only thing, we have additional dimension here. And yeah, same DIT block is coming here. So yeah, so this video is sent first to the visual encoder, and we have got the compressed video and then converted them into the tokens and passed them to the diffusion transformers. Again, these diffusion transformers will predict the noise only here. So again we'll predict the noise only, and that noise will remove from the original image, means original image for this here. So here original image for this is like noise image. So from that noise image we'll remove this predicted noise, and we'll generate the try to generate the original video. So yeah, there must be some changes here. This is actually not known till now, but this is overall um, architecture predicted for this Sora model. They are using DIT, that is for sure, and they are using some encoder here, VAE known to be, and this compression technique they are using both temporally and height and width wise. So these things are happening.
So that much we know is uses DIT block, but what
Yeah.
changes to DIT we don't know, because they are keeping it still secret, right? So
Yes.
and but textual, textual prompting would also be there, right, in the DIT.
Yes.
So I'll say, okay, a man walking in the park, right? So it will generate a video as per that, a man walking in the park.
Yes.
Okay.
So
Now
But for
it's
Sora,
basically 1 minute video. So something is limiting its capability to produce more than 1 minute video.
yeah, maybe some context length. Maybe I feel
Yeah.
it's losing its context of beyond that. So
I
this part are
think
yeah.
somebody was asking a question. Go ahead and ask your questions, please.
Right, just for understanding purpose, I was thinking the input is text, right? But in this architecture, it's been shown.
So this is a training process actually.
Oh, okay.
Yeah.
Okay,
During
got
the
it.
inference, we'll remove this first part. We'll just pass the input text video and some latent noise image as input to the DAT directly.
The inference pipeline is only the bottom part. So during inference, the only input needed would be the textual prompt.
Yeah. So this is about the overall architecture. It looks similar to the DIT what we have discussed in our previous step. So yeah, let's move out for the further topic where it is like how they have generated the training data actually. So we can easily get the videos. There are many outsourced videos that we have. The main thing is like uh, captions for that video. So we need detailed captions for training the model. So actually, um, if we like for generating an video in image in the stable diffusion, we need to pass along with that textual embeddings. So the same thing that we need to do it for the videos. So but maybe it is highly impossible for the humans to sit and write, generate the textual captions for each video, and they must be very clear, and then like more it should have more details. So even like it should explain the backend. So if there are like people walking in the background, or maybe like street lights are there in the background, so those are all everything should be clearly mentioned, so that the model the our Sora model also will learn that complete detailed related things, and then it will be able to generate more detailed video, as we have seen in the some example videos where it was having more fine details also captured. So in order to do that, we must have the training data as is. They have generated these captions for each video in their data set using the captioner model. Yeah, this is actually not known. This is complete black box till now. Once they release this research paper, maybe we'll come to know. So this is one model which will generate the captions for the videos, and detailed captions it will generate. So once it generates the caps, like we have now X for the training process, wherein like textual prompts and then videos for now. So here we can see like we have videos and we need the textual prompts also. Those two we have now. So for this purpose, they have use this captioner model. And even like during the inference time also we need the captions. So we as a human being, so while asking model to generate some video, will might say just single line or some 2 3 words to generate video. But internally they are invoking GPT model to elaborate that our prompt, to elaborate and then generate a clear detailed prompt and then pass it to the Sora model. So that is what it is mentioned. So like backend GPT is getting used for elaborating our prompts. So once we elaborate those prompts, we'll pass them to the model here, Sora model, during the inference process for now. And during the training process, they are using their own model for generating detailed videos.
Jani, video captioning is a pretty old algorithm, right? So,
Yeah, yeah.
so it
So
was not difficult to.
must have using existing one only, but not disclosed.
Yeah. So, but the additional thing they are having to do is, because the caption it generates,
Yes,
would be primitive or basic. So they are using GPT to convert a short form caption into a long form descriptive caption, right?
yes,
Because that would describe the frame image in much more detail.
yeah.
Okay.
Yeah. So that's why they have given that they are using GPT for getting the details of the short prompts. Yeah. So that is about main thing, the training data and then the architecture of the Sora model. So it is more or less like a DIT only, not without much changes. And these are all things we have seen in our previous slides. So hope everyone understood clearly like how it is possible to train this DIT model for videos. Then like if you see the differentiator parts in when it comes to the Sora model. So earlier models were having some tight bounds like they were able to maybe generate 4 seconds videos, or they'll be able to generate only 256 by 256 size of kind of videos. So if you say, if you take latest our model from Google, Lumira, Lumeire. So that is like it is able to generate only 6 seconds videos, and its size is of around 512 by 512 size. So that is that kind of restrictions we have. But when it comes to the Sora model, it is able to generate 192 by 1028 size images of widescreen, and vertical size of 108 by 1920 size image. And also it is able to generate anything in between. So maybe like if you ask for 512 by 512 size kind of image, it will be able to generate. And maybe like 1024 by 1024 also it will be able to generate. So this kind of flexibility it has. So this flexibility it got because I'm thinking that the transformer model that we are using as an architecture, since like a transformer block is same, like if we have an image of a larger image, we'll pass it like maybe some 100 times. If we have a smaller image, we'll just pass it like maybe 32 times. So even like whatever maybe the number of tokens that we have, that the block change, like transformer block, we don't need to change anything. But when it comes to the unit based or CNN based models, the input size must be fixed. So that is what I think this is making helping here to generate what of any kind of any size of image. So yeah, as we are generating this kind of as we are able to generate any size of videos, so sometimes we need to quickly generate some sample videos, very small videos, maybe like 62 128 by 128 by 128 by 128 kind of videos, and generate check our video quality. So if you like that, then we can try to generate some bigger images, bigger videos. So that will help here. Instead of directly generating 192 by 1080 kind of image, we sorry video, we can generate some smaller videos and verify it. So if you like that prompt, then we can save that prompt and then try to generate same video in a bigger space. So this kind of help we have after using this transformers architecture in the backend. And we are also able to generate both text to video kind of text to video generation, and also we are able to generate image to video as well. And also video editing is also possible. So these are all few different things happening. And Sora is able to generate around 60 seconds video. Even like till now Google has was able to generate only 6 seconds video, Google Lumira model. And the quality is also the thing compared to the competitors like Runway by ML, and also other other models available in the currently. The quality is also quite high. They are not able to match the quality of Sora, along with the size and then
Yeah.
duration of the video.
So there is something called lava as well, I think.
Lava. Okay. Not sure. I've seen Google one, and then we have Runway by ML, and there is stability. From stability also we have one video generator, and that is even like, yeah, kind of animations only. Even still, I guess stability from stability AI, and with this we can generate the video from the text to video and also image to video as well. We can give image as input, and then we'll try to generate the video as well. Yeah, let's look at the use cases. As we know that it can generate text to video and image animations. We can generate, we can just input one image, and we can generate the animation out of that image, and we can make the videos continuous. This we'll see some example to understand, and we can edit the videos, like changing the backgrounds, and then some changes we need to do, that also possible with the Sora model. So this part, let's see some video for understanding better. So actually, Sora has been given two different models, two different videos. So let's see the input one. So this is the input one, wherein like we have one building of top view. Yeah, this is another video of Christmas uh, kind of thing, Christmas celebrations. Now Sora has combined these two videos and seamlessly, and then created one new video. So you can observe this video here. Slowly from top view of the building to it moved to the this part of the video. We can't differentiate that these two are different videos, and then they both are not part of the same thing. This is completely of different world, and then this is of completely different world, but it has combined these two so well, and then generating this kind of video.
Hmm. So combining videos, not overlaying the video, but combining.
Yeah, continuation kind of thing
Uh,
from this. Yes.
Destination back to back.
Yeah, without any lag or some kind of distractions.
Hmm.
Generally, for an video generator, I think this will be very hectic task, I guess, for human beings. So let's see the other videos. So there are some limitations as well. Not only it is not only able to generate this kind of quality videos, there are some limitations like this, where people might have already seen this. So here we can see that this basketball net got destroyed, but again it got into its original shape, uh, because it doesn't have that uh, currently Sora is not following this physics properly. If you have seen some kind of videos, like there are two or three wolves in the video, suddenly the fourth one will get fourth one will come out from the stomach of the another wolf. So that kind of physics it is not able to follow. So these kind of video things are there, limitations. It is able to generate video, but sometimes there won't be any logic behind that.
Right.
Yeah,
Interesting.
so these are the limitations of Sora. Yeah, yeah, this here we come to the end of our presentation on Sora. So I hope everyone understood about the stable diffusion and then diffusion transformers. So that's pretty much same thing is used in the Sora. Anyone, if
Very
anybody
nice work, Jani. Audience, any questions? So as to the slide, I suggest, you all can join our AI Lab community. So reach out to us if you want to join our community. I'm not saying that slides are always given, but based on the presenter's discretion, slides and notebooks are given to our community members. So if you want to join our community or want to collaborate on general R&D, reach out to us, which is Vivek. I'm Vivek, and my number or WhatsApp number is provided in Google Chat here. We do invite you to join our community for collaborative R&D. Any other questions for Jani? Interesting session on extremely state-of-the-art technique called Sora, which was, I think, released like a week back by OpenAI. Any other questions? Okay, so thank you all. Thanks, Jani. Very good session indeed. Good research on very nuanced new topic. With that, we come to the end of this session.